Logistic regression. We have already learned about regression models. Specifically, we learned about linear regression model and multilinear regression model, which they are used to make prediction for the outcome of a continuous random variable. A logistic regression model, however, is not a typical regression model because it is used to make a prediction for the outcome of a binary variable, or can be extended to make a prediction for a multi-class variable. So the dependent variable can be a categorical, despite other regression models. Therefore, it is a classification technique. Logistic regression can be used to make a prediction for the probability of occurrence of a binary event utilizing a function that is called a logistic function, a logit function, or a sigmoid function, which we're going to learn about it later on. It is a special case of a regression model where the target variable is categorical in nature. Logistic regression is one of the simplest and commonly used machine learning algorithms especially for binary class, two classes, or multi-class classification problems. It is easy to implement and can be used as the baseline for any binary classification problems. Its fundamental concepts are also constructive in deep learning. Logistic regression can be used for various classification problems such as spam detection, diabetes prediction, whether a given customer, for example, will purchase a certain product or not, or whether a user will click on a given advertisement link or not, and many more examples of this sort. Types of logistic regression models. We have binary logistic regression models in which the variable has only two possible outcomes, a spam or not a spam, cancer or not cancer. So it's two or binary. We have multinomial logistic regression in which the variable has more than three or more nominal categories, such as predicting the type of wine. So you can have multiple categories for wine. And also we have what is called as ordinal logistic regression, in which the variable has three or more ordinal categories, such as restaurant or product rating. So here we have numbers. It's nominal data, so it's different from categorical data. Because here we know that, for example, a rating of 2 is better than or higher than a rating of 1. Unlike a categorical data that we cannot really compare them in the same sense. To understand the logistic regression function and how it works, let's actually take a look back at the multilinear regression model. So here we have the multilinear regression model. We have the yi hat, which is an estimation of the dependent variable, the target variable, and on the right we have the coefficients, and we have the intercept b0 and the coefficient b1 and bi multiplied by their independent variable or the feature variables. We show yi hat by hat because it's an estimation, because we actually have used the sample data to find the coefficient b0, b1, and b2, etc. to bk. So how does this work? So as you see here, we have the input feature variables here, and then we have the coefficients. If you multiply the coefficients by the input features, b0 multiplied by 1, b1 multiplied by x1, b2 multiplied by x2, and etc. and so on and so forth, you're going to get this. So this is going to be our output, which is, in linear regression, is going to be a real value. Now we have to think about how can we actually modify this system so we can have use this system to make a prediction instead of a real value, to make a prediction for a binary category, 0 or 1 or whatever type that we have two classes here. So we're going to start with 0 and 1. How can we actually modify this system that we have here to make a prediction for 0 and 1? To achieve such a goal, to transform y, the dependent variable value, into a value of 0 and 1, this is the job of the logistic function or the logit function or the sigmoid function, which is going to transform the real value, the input, into an output value between 0 and 1. So we have a real value here. We want to transform this to a value between 0 and 1. So first thing that we will do is we actually going to transform the value of y into a real value between 0 and 1. 0 and 1. And then, for example, we can make a cutoff point as 50%. If the value is greater than 50% and between 50% and 1, we're going to categorize it as class 1. And if the value is less than 50%, meaning it's between 0 and 50%, we're going to classify that as class 0. So this is the logistic function that we are looking for. This is called the sigmoid function as well. So we're going to use actually the exponential, as you see, exponential function here. And by doing this, this is going to give us a y value between 0 and 1. Now, if you use the cutoff point, if the value that you get, for example, is 68%, then you can classify that input variable as the output to be a class 1. The logistic function, as known as logit function, or as some call it, the sigmoid function. Let's see how does this work. So here we have a linear regression model, a simple linear regression model with this formula here, which has only one independent variable, as see here. And it takes values between negative infinity to positive infinity for the y independent variable. So what we want to do using the sigmoid function or the logit function, we want to transform these values between 1 and 0. So we want to concentrate the output variable between these two values, 0 and 1. The logistic function that you see here is this S shape that we have here. This is the logistic model. So what the sigmoid function does is, as you see here in a S-shape curve, it can take any real values and map them into a value between 0 and 1. If the curve goes to positive infinity, the linear regression line, then the predicted value for the logistic regression will become 1. If the linear regression model goes to negative infinity, then the logistic regression equivalent of that would be 0. So any value would becomes between 0 and 1. We can actually set a cutting point, for example, 50% here, and say that if the y predicted value is greater than, is falling actually above the 50% cutoff point, then we're going to classify those as class 1. And if the predicted value falls below the cutting point 50%, for example, is 49% or 20% or 11% or 1%, we're going to classify that as class 0. All right. So for example, let's see that, suppose that we want to make a prediction using the logistic regression model to see whether a person has a cancer or not. So has a cancer here means positive 1, and not having cancer means 0 here. So suppose that the predicted value is 0.75 using the logistic regression model. It's going to be a value between 0 and 1, right? So suppose that it's the predicted value for our logistic regression is 0.75. So how can we interpret that? First of all, 0.75 is about the 0.5, so we're going to classify that as class 1 or having cancer. But how do you interpret this 0.75 if with comparing to, for example, another scenario where it was 85%, 95%, or 65%? So here, this output actually is a probability. So here we say that there is 75% chance that the patient is class 1, or if you want to interpret it in realistically, would be there is 75% chance that the patient has cancer. If this was instead 31%, then 31% is actually going to fall below the cutoff point. So we're going to classify that as 0 or not having cancer. And then we would say, okay, there is 31% chance that the person doesn't have cancer. There is 1% chance the patient has cancer. And for example, if this was even lower, it was like 8%, then we would say that still it's going to be classified as class 0. So we would say the patient has 8% chance to have cancer. Binary classification using logistic regression. Suppose we want to make a prediction regarding whether students in a class would pass a test or not, given their hours of study. So this would be a binary classification because the outcome would be passing or failing. We only would have two outputs. So here we have output. On the x-axis, we have the study time, and on the y-axis, we have passing and failing. And since this is a binary, that means that we only have people who have passed and who are failed. So there are only these two possibilities. So what we are looking for is we want to use a logistic regression which can compute the probability of passing the exam, and then we can use a cutting point, for example, whatever, 70%, 60%, 50%, to classify the students as pass or fail. Visualizing a logistic regression for two features. Suppose we have two features, feature 1 and feature 2 that you see here. So these are the independent variables. And we have actually two classes as well. We have class blue here, which we can actually show them by class 1, for example. And we have class red, the other class, which I can classify it as class 0. So what we are looking for using the logistic regression, we want to actually invent or come up with a function, the logistic function, of course, that can, given these data, the feature values here, feature 1 and feature 2, of the red data points or class 0, that function would make a prediction for the y to be 0, and for the blue values to make a prediction of the y to be 1. So since we already have two features here, that means that we have two independent variables, and given the y variable, the dependent variable, we're going to actually have to plot this in a 3D. So here we have feature 1 and feature 2, the two independent variable, and the y variable is in the third dimension here that you see. And this is our sigmoid or logistic or logit function. As you see here, for all the blue values, for all the blue data points, the y value for them is 1. That means they have been classified to class 1. And for all the red dots here, red data points here, they have been classified as class 0. And as you see here, the function is S-shape. Let's now dig deeper to see how the logistic regression really works. The logistic regression model uses the odds ratio, which is a representation of the probability of having an event of interest compared with the probability of not having an event of interest. And this is because we are our problem that we are working on is to make a classification for a two-class problem, 0 or 1 problem, a binary problem. So that's why we are comparing the probability of something happening versus the probability of that event not happening. Odds is the probability of an event of A, for example, happening divided by the probability that event A is not happening. Let's see an example. Suppose we are flipping a coin and the coin is actually fine coin. So the probability of getting a heads is equal to the probability of getting a tails. If we define getting a heads as success here or the event of interest, then the odds of getting a success or the odds of getting a heads would be 50% divided by the probability of getting a tails or getting a failure would be 50% divided by 50%, which is 1. So we say the odds of getting a heads are 1 to 1. We can also write it this way. 1 to 1. So the formula for odds ratio of A is shown here. The probability of event of interest A divided by 1 minus probability of A. That means that the chance that event A happening divided by the chance that event A not happening. If we have the odds ratio of A, then we can find the probability of A using this formula. It would be the odds ratio of A divided by 1 plus the odds of ratio of A. So as we see here, using these formulas, we can figure out how the odds ratio and the probability are related. Logistic regression model. Let's now see how a logistic regression function or a logit function or a sigmoid function work. What we want to do basically is to come up with a mapping function so that it could map any values from negative infinity to positive infinity on the dependent variable into values between 0 and 1. In the logistic regression, we're going to use the odds ratio to do that. So instead of going straight forward for the dependent variable, we're going to use the estimated odds ratio. So this is the model. The natural logarithm, ln is the natural logarithm, of the estimated odds ratio is equal to this term right here. B0, the intercept, plus B1 multiplied by x1i plus B2 multiplied by x2i, and so on and so forth. So what we want to do now is we want to find the probability of an event of interest happening, or in the classification term, a binary classification term, it means that finding the probability of this event be class 1. So if you find the estimated ratio, we can do that. So first, let's find the estimated odds ratio. The estimated odds ratio given the previous equation is equal to this. E power B0 plus B1x1i plus B2x2i and so on and so forth. This is the estimated odds ratio. Now that we have the estimated odds ratio, it's actually easy to find the probability. The estimated odds ratio, if you have the estimated odds ratio, the probability according to the previous formula that we learned is the estimated odd ratio divided by 1 plus the estimated odd ratio. That's actually equal to the probability. So having this, we can now find the probability or the estimated probability. This is the formula for general formula for probability, and we actually, if we now just plug in this equation here instead of the estimated odd ratio, we're gonna get the estimated probability. We can further simplify this equation. If we divide the numerator and the denominator by this term, which is the estimated odd ratio, we're gonna get this term, which is a simpler actually way. So this is the estimated probability that we are looking for. This is the logit function or the logistic function. When we train a logistic regression, what we are doing basically is to finding the coefficients here, the coefficients such as B0, B1, B2, etc., etc. So when we train a logistic regression, that's what we do. Let's see an example. A manager of a bank wonders which of the existing standard credit card holders should be targeted for a campaign to persuade them to upgrade to the bank's premium credit card. Data were gathered for 30 customers. There are three variables that we have. We have the upgraded is the Y variable, the dependent variable, and it indicates whether a cardholder would upgrade to a premium card. And since it's a binary, 0 here means no, he or she would not, and 1 means yes, he or she would do that. And we have two independent variables. We have purchases, which is the previous year's credit card purchases in thousands of dollars, shown by X1. And we have another independent variable called extra card, and that's whether the cardholder has ordered additional cards for other authorized users. This variable is shown by X2, and it's a binary variable. 0 means no, and 1 means yes. Given the output in this piece of Excel output, compute the probability that a cardholder who has spent $36,000 last year. So the expenditure here is $36,000 and possesses additional cards for other authorized users would upgrade to the premium card. So here we are looking for the probability of upgrading, which basically means the dependent variable, remember the Y here, which would be 0, no, 1, yes. So we have to find the probability that probability of Y equal to 1 means that the person would upgrade. How should we do that? Well, in the table given here, we have all the information that we need. In the first column, we have the definition or the description. So the first one is the intercept. Then we have the purchase variable, which is the X1. And then we have extra card, which is X2. And the next column, we have the coefficients. So B0, for example, the intercept is negative 6.9394. The purchases is the purchase coefficient, the B1, which is the coefficient of X1, is 0.1395. Extra card coefficient, B2, is 2.7743. So we have all the coefficients that we need. We can build the probability using the previous formula. We can actually find the estimated probability of Y equal to 1 or the person would upgrade. So given this information, try to use the previous equation to find the probability, and then we're going to see the solution later. Let's now see the solution. So what we need to do, we need to find the natural logarithm of the estimated odds ratio, and then we're going to plug it in the formula to find the probability. So first, let's go to this. The natural logarithm of the estimated odds ratio is B0. This is from the table. If you can get the table here. So this is B0 here. Then plus B1 multiplied by X1. B1 is given here. Plus B2 multiplied by X2. All right. And we also have X1 and X2 in the X1 is 36 and X2 is 1 because the person has actually ordered extra cards. Okay, so if we plug in these numbers, we're going to get the natural logarithm of the estimated odd ratio as 0.8569. So the only thing that you need to do is to plug in these values here, and you're going to get 0.8569. So that's the estimated odd ratio. Now we need to plug in this into the estimated probability formula, which is the estimated odd ratio divided by 1 plus the estimated odds ratio. So if the natural logarithm of the estimated odd ratio is 0.8569, then you can find the estimated odd ratio. The estimated odd ratio would be e power 0.8569, which is 2.3558. So the odds ratio are 2.3558 to 1. Now that we have the estimated odds ratio, we can plug it into the formula, the probability. So that would be 2.3558 over 1 plus 2.3558, and that's equal to 0.702 or 70%. So the probability that the person would upgrade to the premium credit card is 70%. And if we actually have set up the cutoff point to 50%, we're going to classify this person as would upgrade or class 1. All right, let's do another practice problem. Given the following logistic regression model, the natural logarithm of the estimated odds ratio is equal to 0.1, that's B0, plus 0.5 multiplied by X1, plus 0.2 multiplied by X2. So this is the logistic regression model. Part 1 of the question, if x1 is equal to 2 and x2 is equal to 1.5, compute the estimated odds ratio and interpret its meaning. And part 2 says compute the estimated probability of the event above, where x1 is 2 and x2 is 1.5. So please pause here and work on this problem. Try to find a solution for part A and part B, and then move on to see the solution in the next part. Let's now see the solution. So what you need to do is, we have this formula here. This is the logistic regression formula. The natural logarithm of the estimated odd ratio of the event of interest happening is equal to 0.1 plus 0.5 x1 plus 0.2 x2. If x1 is equal to 2 and x2 is equal to 1.5, compute the estimated odd ratio. The estimated odd ratio, this is what we are looking for, and interpret its meaning. So the only thing that you need to do is to plug in these numbers into the equation. x1 equal to x1 equal to 2 and x2 is equal to 1.5. And if you do that, you're gonna get the natural logarithm of the estimated odd ratio as 1.4. This means that the estimated odds ratio is e power 1.4, which is 1.055. So that's the estimated odds ratio. And how to interpret this? This means that the estimated odds ratio, the odds of the estimated odds of the event of interest happening is 1.055 to 1. Next, let's move on to the second part of the question, part B. Compute estimated probability of the event above where x1 is 2 and x2 is 1.5. So this asks for finding the estimated probability. Now that we have the estimated odds ratio, you just have to plug it into this formula here. So that would be e power 1.4 over 1 plus e power 1.4, and that's equal to 80%. So the estimated probability of the event of interest happening is 80%. That means that we are 80% sure that the event of interest is going to be a class 1. So if the cutoff point is 50%, then we would classify this as this example, an incident, as a class 1.